Okay, sorry about that. So, um, I guess what I'm going to do is this is going to be video part B, since I don't know how to splice them together. And I looked at what I just recorded and could see sort of where it went out of focus. So I'll try to start about then. And so I'll be uploading two videos, a part A and a part B, um, today or tomorrow. Not sure when. Okay, so. Going back to, I mean, basically where it started to go out of focus, and to a certain extent, maybe I can take my glasses off so I can keep an eye on what's going on the screen there. That what I explained is that when you forward bias the diode, right, that causes holes to, because the barrier is lowered, to flow over on this side, and so you have this higher concentration of holes on this side above the equilibrium concentration, Pn0. And so you can basically think of it as I put the bias on, it goes like this. And the same thing on the N side, okay? It basically starts going like that. And I'm going to label this N sub P for now and that P sub N, just to have something to label with. And we'll talk about what that is in the next lecture. Now, this is called diffusion current analysis of a diode, because what's going on now is that there is what's called diffusion current. And diffusion current, now we have to sort of, we're going to take it an aside, and we're going to back off, and we're going to talk about diffusion current. So some textbooks and other ways of doing this course would be to have talked about diffusion current several lectures ago. But I chose to do it this way because this is the first time it sort of comes up where you need to worry about it. And I always felt that I always learned things better when I learned about them when I needed to, rather than ahead of time and going, you'll need this someday. Now I can see I need to do it. Because, okay, if you think about it, let's focus on the P set over here. I have a gradient of holes. And what that means is that if you ever have a gradient of something, if I have a gradient, well, I'm trying to think of a good example, but let's say of blue dye, right? Okay, if I have more blue dye on one side than the other, I'm going to get blue dye flowing in that direction. It's kind of along the lines of nature abhorring a vacuum. Basically, if I have more holes here than I do here, holes are going to want to move in that direction by diffusion. If you really want to get purist about it, I mean, what's basically going on here is that I have more holes here, and diffusion is just what it sounds like. It's moving in all directions. And so I have components of holes moving in that direction as part of my diffusion. Over here, there's a smaller component of that, and so net, I get holes moving in that direction. And, diffusion current is pretty easy to understand. Basically, let's stick with holes. If I have some gradient, some change in P with X, then there's what's going to be called a flux F of holes that's equal to negative dP dx. Why the negative sign? Because if you think about it, the slope here is negative, but holes are definitely going to move in that direction because there's more here than there. And I left out something, times the diffusion coefficient, which for now you can just think of it as a proportionality constant. Okay, now, so basically the flux. Now, what is flux? Flux is the carriers. I guess we should have written holes since we're talking about holes. per unit area per unit time. And, and then if you think about it, since J is the charge per unit time per unit area, right? Because charge per unit time is I, that's equal to this times the charge of an electron. And so we can talk. I mean, I could label. I could put diffusion there. It's basically a current density due to diffusion, which is due to a gradient in concentration. Now, let's think of a couple of cases here. All right. Let's make P linear. Okay, if P is linear, then F, which is minus d dp dx, is the same. All right, in both those places. Whereas if P is not linear, okay, then F is higher there. Now, if you think about it, there's a big consequence then of, okay, if P is just a straight line versus X, then it's kind of boring because it just means that the flux is the same everywhere. Okay. Now, if F has curvature, if P has curvature to it though, if you think about it, if this is X, and this is X plus dx, then F there, because it's that, is going to be bigger than F there. Because the slope there is bigger than there. Now, that's a serious issue, right? Because if, it's checking my focus, if this is some very, this is basically a differential dx. And what this is saying is that in this differential box here, there's more going in than's coming out. Which means that the number of carriers inside that differential has to be going up with time. All right, which is a serious problem because if you think about it, when we forward bias a diode, right? All right, we get some distribution of P. That can't be changing with respect to time. It wouldn't make any sense because once we forward bias a diode, I mean, if you ever did it in one of your circuits labs, does the current change? No. Okay, so nothing is changing with respect to time. Okay, once we forward bias it, it makes a distribution, and then that's it. It's not changing. The fact that I drew this with a curvature to begin with implies something else is going on here, and we have to determine what it is. Because these distributions are independent of time. We call them steady state, which I'm not going to write down because I don't want to, go into too much. But you just sort of realize that these are independent of time. So when I have a curvature in there, okay, in this picture, okay, P would be going up, except something else is happening, and that something else is recombination. Now, recombination is something we can spend a lot of time talking about, and we might. But for now, the way to think about it is that going back to our picture over here, at any given point in space, there's excess holes, right? There's more than an equilibrium. Well, if there's ever any excess of something compared to equilibrium, they want to go away. And how do they go away? Well, there's electrons out there, right? So they want to recombine with those electrons. And so what's happening is that, okay, let me just write it out. So dp dt, all right, now I'm just going to write it down, and you have to kind of think about it. All right, so what that's saying. Now, if I don't have any recombination, then we're not in steady state, and P would be going up there. Now, I wrote it out this way, and you have to think about it a little bit. And it perhaps would have helped if I would have written it, you know, this way. I would have put the dx over here first. Actually, what I'll do is I'll insert it there. Okay, because if you think about it, this is the carriers per unit area per unit time, right? And it represents how much they're going up in that little differential. P times dx is, remember, P is per unit volume, so when I multiply times dx, that's the carriers per unit area. So the change in time of the carriers per unit area, which is PDX, is equal to the difference in the fluxes going into the box and out of the box. And so now I'm just going to put that back there where it belongs. And that's 0, okay, and the reason why it's 0 is that it identically equals to the recombination. Now, so more carriers are going in by diffusion than are going out, and something's happening to them. They're recombining, and recombination we write this way: P minus Pn0 over tau. Now, what is that equation? What is this telling us? That's telling us that if I have excess carriers above the equilibrium level, they will tend to go away. And this equation is saying the difference in the fluxes is exactly equal to the carriers that are recombining inside that box. Now, what is tau? Tau is the recombination time. We may circle back if it's warranted to talking about recombination more and why it's proportional to the excess carrier concentration, why it's proportional to 1 over the recombination tau. For now, you can see that the units are come out right. And when those two are equal, then this is 0. Okay, and now, okay, we can do something neat, because we can write then that 0 is equal to, what is this? This is df dx. I'm going to start, well, no, now it isn't df dx, it's minus, right? Because df dx would be that one minus that one. And that's equal to P minus Pn0 over tau. Now, what is F? F is d times dp dx. So I can insert that there, and then I get that's equal to d times the second derivative. And this is sometimes called the diffusion equation. It basically tells you how P can exist with respect to D and tau. And sometimes, and you know, I mean, you guys can just watch this. What you do is you put L squared there, where L is defined to be the square root of d tau. And that way, and L is sometimes called the diffusion length, and so it kind of just makes everything very simple. Okay, so the good news is we now have a differential equation describing our carrier concentration. And it's a second order differential equation, and the solution is pretty simple. It's like all differential equations in a sense. You don't know the answer until you write it down and you check that it fits, but let's go ahead and do that. The answer is basically P, let me write it a little bigger, P is equal to Pn0 plus A. Now what is A out? A is from our boundary condition. E to the negative x over L. Now, I wrote it down that way to start with because you know, it sort of allows you to see it a little more cleaner. But I'm going to make a slight change to this, just because it'll make our lives easier when we calculate the boundary condition. I'm going to put x minus xn over L. Now, all I've done there, it's still e to the minus x over L. It's just I sort of made A a little bit different. And you can kind of understand where I'm going because my boundary condition is at xn. And so it just makes it more simple to write it out this way. Now, check that it works. Okay, d squared p dx squared. Now think about it. Okay, I take two derivatives. So I get two L's in the bottom and the minus I canceled. So I get A over L squared e to the negative x minus xn over L. Right, that's the second derivative. And if you look at it, that's equal to p minus pn0 over L squared. Because p minus pn0 is A times that. So it's right. All right, so now we're almost done because now I know over here that P is Pn0 plus A, which is something I have to figure out, e to the negative x minus xn over L. And to calculate A, I just, P of xn is equal to Pn0 plus A. Right? See, that's why I did that. Because now when I plug in xn, that becomes 0. And so e to the 0 is 1. Now what is that equal to? Pn. Okay, sorry. So A is Pn minus Pn0, and P of x is equal to Pn0 plus Pn minus Pn0 e to the negative x minus xn over L. Let's stand back and look at that for a minute. Make sure you understand this plus. So at x equals 0, or at x equals xn, that's 0, so e to the 0 is 1, and p of x is pn0 minus pn0, so it's pn. Now at x equals infinity, this is e to the minus infinity, which is 0, so that goes away, so it becomes pn0. So it's basically this exponential going down. And the same thing happens on this side. Now here, okay, what people usually do is they redo a coordinate system kind of with x in that direction, just to make it sort of simpler to understand. And n of x then is equal to np0 plus np minus np0. And okay, I mean, I could write it for x negative, but just x minus xn over L. Now, we do have to be a little careful about something here, which is that the diffusion lengths for electrons and for electrons and holes can be different. So I forget what did we use as a subscript? We just used n and p. So over here, since that's for electrons, we write n, and then we write p over here. Okay, that's where we're going to stop today, and hopefully it wasn't too much of a disruption to have to view 2 lectures. This constitutes 1 lecture. Basically, the lecture today is determining the minority carrier distributions when you forward bias a diode. Now you can kind of see where we're going, which is now that we know the minority carrier distributions, we can calculate J, because it's this. And so really the next steps are pretty straightforward. It's just I wanted to stop the lecture here so that you really have a good grasp that what we're doing is we're finding these minority carrier distributions, and then the next step is pretty quick, but then we can talk about it more and sort of stand back from the equations a little bit and in the next lecture. Okay, that's it for today. Thank you.